Hello, everyone. Welcome to this lecture at the part of the MTV Summer School. For today, Carrie will be giving a lecture over neutron detection. Carrie-Ann is a first-year PhD student at the University of Michigan. She has a Bachelor's of Science in Nuclear and Radiological Engineering from Georgia Tech. She works in radiation detection and measurement under the joint direction of Dr. Putzi and Dr. Yovanovich. She specializes in active interrogation.
Yeah, thank you so much, Ethan. All right, I'm gonna go ahead and share my screen and we can get started.
Also, as we go through the lecture, be sure if you have any questions, you can post them in chat and we can discuss them from there, answer them as they pop up, or whenever there's a good time to answer those questions.
All right. Hey everyone, as Ethan said, my name is Carrie-Ann and I will be talking to you guys today about neutron detection. So first I want to go over some applications of neutron detectors and why they're important. So thermal detectors can be used to monitor the flux of a reactor because flux is proportional to power. So that's a really important application. Neutrons are also a very unique signature of nuclear material. We're talking uranium and plutonium here. Other things don't really emit neutrons. So we can use neutron detectors to make sure that fissile material is accounted for. This is in a lot of ways implemented in the International Atomic Energy Agency's safeguard regimes. So think like enrichment plants, spent fuel, parts of the fuel cycle where it may be easy to divert material for non-peaceful purposes. And I think like towards July or August, like the end of the summer, there'll be a more specific talk over like what the IAEA does. We can also apply the same principles to Homeland Security. So oftentimes the Department of Homeland Security will set up portal monitors, and these contain either scintillators or helium-3 to detect neutrons at borders and ports to prevent smuggling sources in and out. And then this is what they look like. So they're like these huge panels. But you can also use these at labs to monitor for contamination as well. This isn't usually how it's done, but it can be used to do that also. So we talked about this pretty extensively yesterday, but the probability that a neutron undergoes a reaction is highly dependent on energy. So for this reason, we're gonna split the neutrons up today into two different groups. And we're gonna set the two different groups with the cadmium cutoff. So this is the cadmium cross section, this red line here. And you can see right at 0.5 EV, you get this spike and then it drops down. And the cross section for capture is a lot lower. And so that's where we're going to set the cutoff. But essentially, we're going to consider a flow neutron anything below the cadmium cutoff, and a fast neutron will be anything above 0.5 eV or anything above the cadmium cutoff. And so all neutrons are born fast. The average fission energy for a neutron from uranium-235 and also californium-252 is approximately 2 MeV. So that's a lot higher than this like 0.5 EV cutoff. And neutrons are moderated in the environment. So here I have the average number of collisions it takes to thermalize a 2 MeV neutron. So as you can see here for hydrogen, this has approximately the same mass as a neutron. It'll take 27 collisions. And then when you get up to heavier and heavier materials, it'll take more collisions. Uranium, it takes thousands of collisions to moderate it. And that's just because they're so much bigger, the neutron can't deposit as much energy on there. All right. So all the things that we have discussed detecting right now have Coulombic interactions in detectors. Alphas and betas are charged particles, and then gamma rays cause the atom to emit electrons, whether that's through the Compton effect, the photoelectric effect, or pair production. Those are all interactions that can happen, which will create electrons in the detector, essentially, which are charged particles, and that's how the signal is created. So what we have to do with the neutrons is they need to interact in the detector material in a manner that causes ionization. So flow neutron detection is typically done with absorption reactions. So the neutron will be absorbed and a nuclear reaction will occur, and this will transmute the target nucleus into a product nucleus, and then like a proton, an alpha, a gamma, or if it's like fission, you'll get fission fragments and more neutrons. And then we can do a couple of things to detect fast neutrons. So the first option, and maybe the more obvious option after we just talked about how slow neutrons are detected, is that we can moderate the fast neutrons to thermal energies or to slow energies, where the cross sections are much higher, and then they can undergo the same reactions that the slow neutrons undergo. Or we can detect the fast neutrons through elastic scattering. And the neutron will scatter off of a nucleus and deposit some energy, and then that nucleus will cause ionization or scintillation in the detector. And then we can also, I'm not going to go into this too much, but you can also detect fast neutrons with threshold reactions. And so a high energy neutron will cause a reaction that produces a proton or an alpha or something like that. These are different than the slow neutron reactions we're talking about because these reactions are endothermic. So the neutron needs sufficient kinetic energy to allow this to happen. So the first absorption reaction that we're going to talk about is radiation capture. So the atom will absorb a neutron, causing excitation, and then de-excite via a gamma ray. So this is an example of this. Plutonium-239 absorbs a neutron. It becomes plutonium-240. So it's the same element, just a different isotope, and it will emit a gamma ray to de-excite. And then there is capture transmutation. So the atom absorbs a neutron, causing excitation, and de-excites by emitting a particle such as an alpha or a proton or something like that. So this is lithium-6, and it will absorb this neutron and de-excite by emitting an alpha. So then that becomes a tritium. And then there is induced fission. And so based off of a lot of the questions we were getting yesterday and stuff, it seems like you guys are pretty familiar with this already. But the atom will absorb a neutron and it will de-excite by splitting into fragments and other more neutrons. So this is uranium-235. It absorbs the reaction and it ends up splitting. These aren't the same every time. This isn't the same number of neutrons every time, but this is just an example. All right, so in capture-based detectors, neutrons will be captured and produced heavy charged particles, and or recoil nuclei. So the total momentum of the products will be zero. This is because the reaction is exothermic, and the energy of the incident neutron is very, very small compared to the Q value of most of these reactions. So the energy imparted to the products is basically equivalent to that Q value. The products will be emitted in opposite directions because of the conservation of momentum, but this is also important when we discuss the shape of the spectra from some of these detectors. Here is an example reaction. We'll talk about it a little bit more in a couple slides, but just so you get the idea. So this is boron 10, and it absorbs a neutron, and it will create a lithium 7 or an alpha particle in one of these two pathways. This one's the excited state. But as you can see in this picture, it's showing them emitted in opposite directions. Okay, so these are the most common capture-based detectors. This isn't an extensive list, but these are the main kinds that you'll like if you take a radiation detection class, you'll spend the most time talking about, or that you'll maybe like see used the most frequently. So this is a BF3 proportional tube. It has that same reaction that we just talked about. It's filled with gas. The cons to this are that the gas is really hazardous. This is a boron line proportional counter. So the outside of the detector has a like thin layer of boron, and then the inside of the detector is just like a pretty standard proportional counter fill gas. This is the helium-3 proportional counter. This is often considered the gold standard of capture-based detectors or of neutron detectors. And this is just because it has really high efficiency. It has good gamma radiation discrimination. The gas isn't toxic. And so that's kind of like for many years, it's been considered the gold standard. And then over here, I've shown the cross sections for all three of these, and you can see they're pretty high. I kind of circled around where I thought the thermal energy range was, and you're seeing that they're like 10 to the 3, 10 to the 4 barns range. Yeah, so going over the BF3 proportional tube first, this is the reaction. So 6% of the time it will produce lithium 7 and an alpha particle with a Q value of 2.79. And the other 94% of the time it will produce lithium 7 in an excited state. And then also an alpha particle, and it will impart this Q value of 2.31 MeV. So when you have this reaction with 2.31 MeV, the energy of the lithium will be 0.84 MeV, and the energy of the alpha will be 1.47 MeV. You can do this math yourself, and Ethan went over how to do it yesterday. But essentially, more energy will go to the lighter alpha particle to conserve momentum. So you can see the reactions happening right here in the tube, and the products are emitted in equal and opposite directions in the center of the gas, like in the center of the tube, and they're stopped in the gas. So let's say that this detector is really big and the walls are far away. Your spectra will look like this. So you get this peak from the reaction that happens 94% of the time, and you get this smaller peak from the reaction that happens 6% of the time. And we can see very clearly that both the lithium nucleus and the alpha particle are depositing all of their energy into the detector. And then what you'll also see is you'll see this line here. This will be a reoccurring theme throughout capture detectors. But essentially, gamma rays can still interact with this gas and cause electrons to like create some signal. But the range of an electron in the gas is very large, and so it will not usually deposit all of its energy. So like if you're like using this in like a lab setting or something, you can like set like a pretty like low energy line to discriminate from gamma rays and neutrons. Now let's say this happens in a really small tube. The particles may escape the detector before they deposit all of their energy. which causes the wall effect that you see in the bottom picture right here. So you get this portion of the spectrum from when the lithium deposits all of its energy, but the alpha particle escapes before depositing all its energy. And then this part of the spectrum is when the opposite happens. So the alpha particle will deposit all of its energy, but the lithium may escape before depositing all its energy. And then you still have these two peaks from when both reactions fully deposit their energy. All right. And so the boron line proportional counter has the exact same reaction, but instead of occurring like in the volume of the detector, the reaction is occurring in a layer lining the detector. So as you increase the thickness of this, let me take a step back. So essentially, because of the conservation of momentum and because the lithium and the alpha have to be emitted in opposite directions, only one of them will make it into the body or the active volume of the detector. And so really the maximum energy that you're going to see deposited is 1.47 MeV. That being said, as you increase the thickness of the boron layer, the neutron will be more likely to interact. So this will improve efficiency. However, the reaction products will lose more energy as it moves in the direction of the detector. So it'll be attenuated some and it won't deposit as much energy in the detector. So it's a really important to balance these two things when you're thinking about these detectors. And so as you can see on the spectrum, 0.84 MeV will be deposited if the interaction occurs right here and all the energy of the lithium is makes it to the detector. But if the interaction occurs right here and the lithium is shielded so much that it doesn't make it into the detector, maybe like even like no energy may be deposited into the detector. And you can see this reflected in the shape of the spectrum from this detector as well. So this is another kind of capture detector. So this is a lithium iodide scintillator. It is lithium 6, and it will undergo a capture reaction and create a tritium and an alpha particle. The Q value imparted on this would be 4.78 MeV. And so based off of the range of these two particles and the standard size of the detector, we don't really see wall effects with this one. And that's like, think about it, like lithium iodide is a fairly similar composition to sodium iodide, and iodine's pretty heavy relative to like these gases that we've just been talking about. So that's kind of why that happens. But lithium iodide has a similar composition to sodium iodide. So if you add just a little bit of europium to this, you can get really good light output. But what I'll say is that gamma rays do interact with this. And because we were kind of like talking about the density, they are going to deposit energy and it will be more difficult to discriminate than some of the things we talked about earlier. And the gamma rays are going to produce a pulse height proportional to the energy deposited versus when the neutron interacts and deposits 4.78 MeV, the light output for that will be 4.1 MeV EE on the same scale as gamma rays. So here is a picture of like what those spectrum look like. It looks like this pulse height is in an arbitrary unit, but if it were light output, this should be 4.1 MeV EE. With the PUBI source, I guess when I was like looking at this paper, it said 0.6 gammas were released for every neutron versus this radium beryllium source, it said like 30,000 gammas were emitted for every neutron, and you can like really like see that there. Yeah. All right. And then this is what I previously called the gold standard of radiation detectors. This is the helium-3 proportional counter. So it works the same as a proportional counter. It works the same as the BF3 proportional tube we talked about, but instead this time it is just filled with helium gas. And so the helium-3 undergoes this reaction. It absorbs a neutron and it produces tritium and a proton. And 0.764 MeV will be imparted on the proton and the tritium. So the proton is much lighter, so that'll get most of the energy, and that's 0.573. And the tritium will get 0.191 MeV. And you can see the spectrum, and it has the same characteristics kind of as the BF3. So this is when the tritium fully deposits its energy, but the proton loses or escapes the detector. And this is when the tritium escapes the detector, but the proton deposits all its energy. And then you have this full energy peak when both of them deposit all of their energy. And so with these proportional tubes, if you mess with the diameter and the pressure of them, you can change the efficiency. This is all about the number of atoms that are in the detector, because if there are more atoms, then it will cause, there's a higher like probability of interaction. So if you increase the diameter but keep a constant pressure, the number of helium-3 atoms increases. If you increase the pressure at the same diameter, number of helium-3 atoms also increases. So both of these will increase the detection efficiency. All right, and then I think this is kind of an exciting idea for a detector. I really like this one. But these are called fission chambers. They're very similar to boron-lime tubes, but they contain a layer of uranium. So what will happen is a thermal neutron will induce a fission. And this like outer coating is highly enriched uranium. And when uranium fissions, about 200 MeV of kinetic energy goes to the daughters or the products that you'll see here. So even if not everything makes it into the volume of this, that's still a crazy amount of energy that's going into the proportional counter part of this detector in the form of fission fragments. And so because those fission fragments are so high energy, it's really easy to discriminate them from gamma rays. These are used a lot if there's a really high flux of neutrons or if there's a really large gamma background. But when there's a high flux, they'll be operated in current mode. So we're not going to see individual pulses. We're just going to see the average current over a certain amount of time. They're also used at power plants and safeguards application. They can be used to measure spent fuel because you can set that discrimination threshold really, really high to discriminate gamma rays because the fission fragments are so high energy. Okay, give me a second. I'm gonna grab some water. All right, so now we are going to talk a little bit about detecting fast neutrons. So I showed you some cross-section plots earlier, and the cross-sections vary highly with energy. So as the neutron energy increased to like past the resonance region, the probability of these reactions occurring decreased. So we have a couple options. There are scatter-based detection detectors, which we'll talk about later. And then you can also thermalize the fast neutrons using a moderator. Um, However, a thick moderator, there can be issues with that. A thick moderator can reduce efficiency. So what's typical is like a couple centimeters of thickness. So this is an example of detecting neutrons with moderators. This is like decades old, but they're called Bonner spheres. So what you'll do is there's a lithium iodide scintillator in the center of these polyethylene spheres. And the count rate in the detector will change based off of the moderator thickness and the neutron energy. Um, so you can see if you have a 12-inch thick moderator, you'll like basically eliminate all these like thermal neutrons, because it'll slow them to thermal energies and then it'll take forever to like diffuse into the detector. Um, but it'll get these like high energy neutrons to the right and to like the perfect energy for this reaction. Versus if you have no bonosphere, you're going to detect all these thermal neutrons, but you'll have really poor efficiency at detecting the fast neutrons just because like that cross section is so much smaller. And then like right, you can set a range. So if you have 3 inches, you'll like get a different range than if you have like 10 inches. And so that's how you do that. And you can apply unfolding to this to get more information about the neutron energy spectrum. This is actually what is used a lot in those like big portal monitors that I showed you on like the first slide or something. But helium-3 detectors will be embedded in a block of high-density polyethylene, and the neutron will scatter to thermal energy and then diffuse into the detector. And so this is what you can see. The neutron comes in and scatters and then diffuses into the detector. What I'll say is that this process takes time. The neutrons thermalize and undergo those scatters really quickly, but it takes like on the order of microseconds for them to diffuse into the detector. So when you do this, you lose information about energy and about timing. So here's just a summary of all the detectors that we've talked about so far. So typically gas-based detectors leverage specific neutron absorption reactions. So we see this with boron, lithium, and helium-3. And these reactions are extremely efficient for thermal neutrons. And you can moderate fast neutrons to a more favorable energy to get it to work in that application. And these reactions release a relatively large amount of energy, especially compared to gamma interactions that will occur in the volume. And so that makes it pretty easy to pick out what interactions are happening from just neutrons. All right, so now let's move on to how we are detecting fast neutrons and why we are. So, as we discussed earlier, all neutrons are born fast. When we moderate to detect them, we lose information about energy and timing, which can be crucial if we're trying to understand the source of a neutron. So these are a couple different neutron sources. The first thing I want to point out is the PUVI source. This is an alpha N source. And this is what the spectrum looks like. The average neutron energy is about 4.5 MeV. And if you were to have energy information about this, this is like a pretty unique spectrum and you could reasonably identify it. Especially compared to like this is Californium 252. This is a spontaneous source, so it has a watt spectrum. Right? And like if you had energy information about the neutrons, you could pretty reasonably identify which source is the alpha N source and which source is the spontaneous fission source. And then this is also really cool, is that this is plutonium oxide. And so it has this alpha N spectrum almost like imposed on the fission spectrum because plutonium 240 has spontaneous fission, right? And so if you get all this information, you can be more likely, you have more capability of identifying a source. and just having more information about what's going on. So here is a refresher on neutron interactions. Another way we can detect neutrons besides capture reactions is elastic scattering, where both kinetic energy and momentum are conserved. If you want to think about this kind of similarly to how we talked about the capture reactions, you can say that the products, like the hydrogen and the neutron, are the same as the reactants, but the reactants are just at a, or the products are just at a different energy. And then in inelastic scattering, momentum is conserved, but the neutron will transfer some of its kinetic energy into excitation energy, so gamma rays will be emitted. So we're going to mostly focus on elastic scattering for this. Ethan talked about this yesterday, but when you have elastic scatter, you have this incident neutron with a given energy E sub n, and it will scatter off of this nucleus with mass m, and this will go this way, and the neutron will go this way, and the neutron will have less energy because it will have given some of its energy to the other nucleus. And so you have this conservation of energy and conservation of momentum equation, and if you solve this equation for the energy of the nucleus, the recoil nucleus, you'll get this answer. If you want to kind of like understand how energy is transferred to the nucleus, think of the neutron as a ping pong ball. And if the nucleus is a bowling ball, the ping pong ball will like bounce right off. The bowling ball won't move. It won't transfer a lot of energy. But if it's another ping pong ball, it can transfer a lot of energy. I feel like that's like the classic example you get in like all your physics classes and stuff like that. So the maximum energy transferred depends on the mass of the nucleus and the angle it scatters at. So you will get this maximum energy transferred when the target nucleus is at 0 degrees. So this would be like the neutron backscatters. And what this does is it effectively removes the cosine term from this equation. Okay, so a lot of times, especially in the labs that I work in, we use a lot of organic scintillators. So organic scintillators are made up of hydrogen and carbon. The neutron will elastically scatter off of the hydrogen and cause the proton to recoil, and this is what causes scintillation. Gamma rays also interact with this type of detector. They Compton scatter off of electrons, and this also induces scintillation. And these are just two really cool pictures of some EJ309s. So gamma rays interact via Compton scatter, which causes a recoil electron, and neutrons interact through elastic scatter, which causes a proton recoil. And in scintillators, when the material scintillates, you have prompt and delayed fluorescence. So light is released in like different time scales, essentially. And the portion of the light released in the delayed component depends on the particle that's interacting. So for this reason, the pulse shape of neutron and gamma ray interactions will be different, particularly in the tail. So as you can see here, the neutron has more delayed fluorescence, so it like releases more light later. So because of this, you can use the pulse shape to figure out if the radiation interacting with your detector is a neutron or a gamma ray. So you can take a ratio of the tail integral to the total integral. So right, if we were to integrate the tail integral, we would take the area under all of this for the neutron and right here for the gamma ray, and then the total integral for each one is just what's in the box, right? And our neutron would probably end up somewhere up here, and our gamma ray would probably end up somewhere down here. So what we do a lot of times is we'll take this ratio and we'll plot it as a 2D histogram. So on the y-axis, y-axis, you have the tail to total ratio, and on the x-axis, you have light output. And then what's happening here is like you've set a threshold, so because usually a lot goes on down there. But you can look at this and like pretty clearly identify, oh, these are neutrons, oh, these are gamma rays. And then you can do a lot of different things to like kind of separate them out. Like you could maybe just like set a discrimination line at like 0.67 and you could say, oh, well, like everything above 0.67 is going to be a neutron, everything below it's going to be a gamma ray. You can fit a function to it and add error bars. And then it also, discrimination depends on the amount of energy deposited, right? Because if you look at this like 200 to 250 keV range, you have two really distinct bands versus like if you look over here around 50 keV, they kind of like merge together. So that's definitely something to consider if you're doing this. All right. And so you detect fast neutrons directly, and the scintillation process occurs very quickly. So because of this, you can tell exactly when the fast neutrons are detected. For this specific still beam detector, actually, I'm getting ahead of myself. But what you can do is you can set up two of these still beam detectors, and you can measure it with a radioisotope that emits two gamma rays at the same time, because those are going to travel at the same speed. So like in this experiment, we use sodium-22 because that decays via positron emission. And it'll create two 511 keV photons and that'll interact with these detectors. And if you detect those photons, you can like run these two detectors in coincidence. So only count it if you detect one in each. And you can plot the amount of time between when the two photons were detected in each detector. And that will give you a good idea of like the uncertainty you have in your detector. So this one has uncertainty of like 1.34 nanoseconds, which is not a lot. That's a really good resolution. Yeah. So organic scintillators are a little bit difficult to characterize because energy and light output are not linear. And I show like a picture of this on the next slide. But what you can do is time of flight measurements. So a spontaneous fission source will emit multiple neutrons and gamma rays. So what you'll do is you can set up two detectors. So this is like your what's a trigger detector, and it's like close to the Californium source. Like I think it's like literally hidden back here, and this is the source. And then this is the detector you're trying to characterize. But there will be a spontaneous fission. A bunch of particles will be released. You'll detect something in here, and then you'll detect something in this detector as well. And what you can do is take the time difference from when you detected in each detector. And so if you have this really small time difference, this is from photon-photon coincidence. But then you like will develop like this lobe from the coincidence between like if you detect a photon in your first detector and if you detect a neutron in your second detector. Yeah. And so what you need to do is you'll need to take this time difference and convert it to light output. But I kind of like breezed over this, but you can do this using kinetic energy. So just E equals 1/2 mv squared, and you know velocity is distance over time. And you can solve for the time of the flight because you know the mass of the neutron. This is like a simplified version of this equation that already includes some of those things. But you can convert this time to light output and MeV and this is what the spectrum will look like. And actually, these are the high energy neutrons because they travel faster, so the time difference is smaller. And these are the low energy neutrons, so you kind of get like an inverse thing going on. And then also, I've been saying this whole time, like scintillators don't have like linear light output with neutron energy, so we need some other function to convert. this is what that means, and this is just due to quenching in the detector. All right. And so then this is a pretty interesting type of detector. This is a helium-4 scintillator. This is different than the helium-3 we've talked about. Helium-4 is just your like party city helium. Um, it doesn't absorb the neutrons, but the helium-4 nucleus will recoil. And just like based off of like the mass of the neutron and the helium-4, the neutron can deposit up to 64% of its energy in one elastic scatter off of helium-4. Um, and then this is like a very common theme in this presentation, but because helium-4 is a gas, it is much less sensitive to gamma rays. So the range of an electron in this detector is extremely large, which is good because that means we can discriminate those pretty easily. Um, and so this is a picture of our detector. It's at 198 atmospheres. I know that's a lot. Um, and then this is, and the diameter is 70 millimeters. So this is the range of the helium-4 recoil, up to 10 MeV, right? So like that is staying in the detector and that's going to deposit all of its energy. Um, but if you have a gamma ray interaction, the electron will most likely escape the detector and not deposit all of its energy. So this is what a spectrum from the helium-4 looks like. So the red is 14.1 MeV neutrons from a DT generator. And you can see like this edge happens right at about 9 MeV, which is 64% of 14.1 MeV. And then you also have a spectrum from a californium spontaneous fission source, and then neutrons from a DD generator as well. And then just for kicks, we have the spectrum of cesium-137. And as you can see, you're not not much is going on there. You're having like some interactions, but this is 0.5 MeV and it's like not even really like depositing more energy than that, right? So you can like see you'll pretty easily be able to cut those gamma rays out. And then also, because it's a noble gas, there is no quenching. And quenching is what causes the nonlinearities and light outputs for the organics we discussed. And so that's huge, and that makes it a lot easier to work with. So Oscar Searfus, who gave this presentation last year, has done all of this work and designed the experiment to prove this. And this is like really cool. And then also the timing resolution for helium-4 is all right. It's about 7 nanoseconds, so it's like worse than that like 1 nanosecond organic I showed you a couple slides ago. But it's much better than the moderated thermal neutron detectors that are on the order of microseconds. All right. So that was like the perfect segue. But talking about neutron timing again, I've showed you guys this already. Helium-3 is what's conventionally used for neutron detectors for timing measurements. They have a really high thermal neutron capture cross section, but they have to be moderated. The scatters happen really quickly, but once the neutrons are at thermal energy, it takes microseconds for it to diffuse into this detector. And then they're also expensive to produce. Helium-3 is from tritium decay, which is produced in the weapons program. This was a huge issue in the 2000s. And then versus organic scintillators have a much lower detection efficiency compared to helium-3. But you have a nanosecond precision understanding of like when the events are happening in the detector. And this improved precision allows for increased statistics and multiplicity counting. Multiplicity counting is basically like coincidence counting for neutrons. So you're trying to detect if like 2 neutron interactions or 3 or 4 or like more neutron interactions occur in a single time period. And so you can just like overall get a better understanding of that. And then they're also much less expensive than the helium-3 based systems. So here's a little summary of the scatter-based detectors. But you can use any isotope whose nucleus can elastic or inelastic scatter with a neutron. The most common ones are organic scintillators, just because you can like deposit all of the energy of the neutron onto the hydrogen atom. Yeah, so like it says, the smaller the nucleus, the higher the maximum possible energy deposition. Um, Organic scintillators are sensitive to both neutrons and gamma rays. Depending on the setting you want to use this in, this can be a good thing or a bad thing. And you can look at the shape of the pulses, particularly the tail of the pulses, to determine which interactions are neutrons and which interactions are gamma rays. And this can be done very quickly with very minimal computing power. And then the organic scintillator light output response unfolding and time of flight information can be used to recover energy information of the neutron source, which is very helpful and can be used to identify sources as well. So thank you so much. And I would like to thank the sponsors and MTV for funding some of this work and also letting me give this talk. And I'm happy to take any questions.
All right, thank you, Carrie Ann, for giving that wonderful talk. So we can go ahead and go through some of the questions left in chat. So Carrie Ann, if you have any questions you'd like to answer first, go ahead.
Yeah, for sure. Yeah, for sure.
So
this question says, how can we detect epithermal neutrons? And it's really the same as detecting fast neutrons, right? We're just considering anything that's like a fast neutron above 0.5 MeV, and anything that's a slow neutron below 0.5 MeV. And so you can use the moderated and then the capture reactions, or you can use the elastic scatter to do that. So hopefully that was helpful. Okay, so this question says, can't we use a gamma detector for neutron detection? And so I'm assuming you're asking about inorganic scintillators. And the thing about inorganic scintillators is that they are pretty heavy. Off the top of my head, I can't remember the atomic number for iodine. I think it's like in the 50s, like maybe it's 53. So the neutron really can't impart that much energy on those like anything like much heavier than like carbon or something like that. And then it also like the range of it is like basically because the stopping power and the linear energy transfer of the like what would be like the recoil iodine in these gamma detectors, like the stopping power is so high, the range is so short that the scintillation states will be like formed too close together and cause a lot of quenching. This question says, why do we need to detect neutrons? There are a lot of different reasons to want to detect neutrons. And my research, personally, what like I've been working on, is I've been working on characterizing the flux of our neutron generator. And so for that reason, we want to understand, like get a better understanding of our source so it can be more efficiently and effectively used for other projects. For safeguards application, safeguards are kind of like a red flag of nuclear material. And if you see that, you know that like nuclear material is present somewhere, and maybe even present somewhere it shouldn't be. So that's that question. Okay, and then this question asks, how long can these detectors be used before it needs replacement, considering that there is a lot of energy happening in it. Honestly, like I don't know off the top of my head, but a long time. Like I've never really like heard anyone talking about like replacing them or things like that. Like there are a lot of like helium-3 atoms in these proportional counters and stuff like that. So
This
this
question,
question,
this question
this
asks
person asks
about
asks about fission chambers with different fissile material. U-238 fission chambers are sometimes used alongside U-235 ones to give some information on neutron energies. Could this be done with other materials? Example, thorium, californium, etc. Yes, it definitely could. I don't think californium would be a good idea, or like plutonium 240 would be a good idea because those like spontaneously fission. But you could definitely like other um fissionable isotopes like will do the same thing and you could use different material. This question asks, what's the main goal behind fast neutron detection? And that's really just because you want more information about the energy and the timing of the neutron interaction. Okay, so I like this question, but it says, why is water used as a moderator? What's the science behind neutrons and water? And so the chemical formula for water is H2O. And so water has a lot of hydrogen in it, which is very good at thermalizing neutrons, because the hydrogen has approximately the same atomic mass as the neutron itself. So the neutron can convert or can basically deposit a lot of energy on the hydrogen atom when it scatters. So it's the same reason that hydrogen is used in a lot of organic simulators as well. Okay, so this question asks about the role of SIPMs or photomultiplier tubes in conjunction with scintillators and how they contribute to signal amplification and processing in neutron detection systems. So a photomultiplier tube um, will couple a photocathode to the scintillating material, and the photons will travel to that photocathode, and when they interact with the photocathode, an electron is produced, and then the electron will be amplified, and that's how the signal is created with a PMT. What happens for a SIPM is it's kind of like a grid, um, and when the photon interacts, it creates like a Geiger discharge, and then like the number of Geiger discharges that occur are like proportional to like to the energy of the photon. It's been a minute since I mostly use PMTs in my work. It's been a minute since I've talked about a SIPM. So it's definitely like not like the best answer. I don't know, Ethan, do you have anything to elaborate on SIPMs?
No, I don't have much to elaborate on in particular about PSIPMs as myself, I mostly work with the PMTs as well.
Okay, so this question asks, what happens to water after neutrons deposit their energy? Is it considered to be radioactive? So for the most part, water is undergoing these elastic scatter reactions with the neutrons. So no, it's not making it radioactive. Um, if like you're talking about like a power plant or something like that, there can be like other interactions that occur in the water that could make it like very slightly um radioactive, but not that much. So it like it just like deposits the energy on the hydrogen. Like it might heat up a little bit if it's like depositing a lot of it. Yeah. Okay, cool. Okay. How can neutron detection help in assessing the enrichment level of fissile material um, in safeguards? I think you're gonna have to do that with either delayed neutron measurements or differential die-away measurements. I can't remember off the top of my head, but maybe like look more into those if you're interested in that. Yeah, so this question says when we calculate the fast neutron dose, we lose some information because we need to slow down the neutron in the first place, and because it's slowing down, the energy is going somewhere else, right? Yes. And so you can get a lot further understanding about the dose because you're like probably in our lab we like have a detector surrounded in a big polysphere, and so like it knows that. And then also dosimeters kind of use like a little bit of different technology, like the dosimeters that like you like will wear on you in the lab. And so like that's actually not exactly the same.
All right, I think we are just at time for everybody who attended. Thank you so much. And thank you so much, Carrie Ann, for giving this wonderful talk.